Hi guys, in this tutorial we're going to look at the limit comparison test and how to use it. And then after that we're going to look at some examples. We're going to look at the three examples showed here. And we're going to see exactly how we use the limit comparison test to prove whether a given series does converge or if it diverges. Now, what is the limit comparison test? Well, for the limit comparison test, what you have are two sequences, an and bn. Now, if we can show that, or if we can have an and bn to be greater than 0 for all n, then this will imply that when we evaluate the limit as n approaches infinity of an over bn, and it actually gives us a specific value, L, such that this L, 1, it is a finite solution, or a finite number, and it is actually a positive solution, then this will mean that if our bn converges, then so will our an. And if our bn diverges, then so will our an. Now, for us to say the state of bn is the same as the state of an, it means that firstly, this condition has to be satisfied. The ratio an over bn, when you get its limit as n approaches infinity, has to be equal to a finite positive solution. And of course, an and bn have to be greater than 0 for all n. Now, what does this mean, and how do we actually use this description to work out questions? Consider these three examples, and for starters, let's pick A. In our first example, we're trying to conclude whether this expression here converges or diverges. How do we do that? Well, as you have seen here, all the question has given us is one series. We don't have an, we can't see bn here. We don't have two expressions, we only have one. Now, whatever the given expression is, take that to be your an. So we take an to be just the argument of that summation. So this is going to be 3n minus 1 over, and then this is going to be n squared plus 1. The first thing that we had to check is our an greater than 0? Well, here, since when you check the summation here, it's from n is equals to 1 to n is equals to infinity. And you can tell to say that regardless of the value of n you plug in there, the solution of an will always be greater than 0. If n is 1, this is going to be 3 minus 1, which is 2. And here you're going to have 2. So this will always be greater than 0. So this condition satisfied. Now, the second thing that we have to do is define our bn here. Now, for bn, all we want to do is to make it as based on this as much as possible. Now, what we're going to do here is, since we're going to evaluate, the summation is being evaluated as values of n are becoming very, very big, you have to see that as the values of n are becoming very, very big, it will mean that it's like the numbers here will not really do anything. From a very big number, when you subtract 1, you'll still have a big number. And from a big number, when you add 1, you will likely still have a big number. So the differences there will be very, very small. Because of that, here, our bn will be selected such that it's just 3n divided by n squared. And of course, we see that this can be reduced so that we end up with 3 over n. Now, you can get it the way this one is, as 3n over 3 over n, or from the start you can get it as 3n over n squared. But again, n is a very big number. When you multiply a big number by 3, you still end up with a big number. So the impact of the 3 there is very, very small. Now, of course, one way that you can look at, you can still work with the way the 3 over n is, but your conclusion, whether you keep that 3 or you don't have it here, your conclusion will still be the same. So what you find in most texts is that in most cases, when you have the coefficient here, a number like that, this number here will not be included, and we just have n over n squared, which will reduce to just 1 over n. So the conclusion we'll have here will still be the same as if you had the 3n over n squared. Of course, all we are going for is not what this limit, it's not what the value of L will be there. It's whether it will be finite and whether it will be positive. And clearly, we see that the 3 here will not change the state of whether L will be finite, and it won't even change whether the L there is going to be negative or positive. So this is why we can just drop that 3. So we just end up with this. So here, what we observe is that we have our two functions. an is that, and bn has reduced to just 1 over n. Once we have the two functions, and you can tell here, of course, bn as well will always be greater than 0, regardless of what the value of n is. Okay, once that has been done, we then move on to the test itself. So we now want to evaluate the limit as n approaches infinity of an divided by bn. Our an is 3n minus 1 over n squared plus 1, and then our bn, I'll just say divided by 1 over n. And then of course, when you change the division to multiplication, let me keep it like this. When you change the division to multiplication, this expression will now become, the second term there is now just going to become n over 1. So this is if you change the division to multiplication. And once you reach this part, multiply these terms, and now we have the limit as n approaches infinity. What you're going to have now is going to be 3n squared minus n divided by n squared plus 1. And then from here, all we have to do now is evaluate this limit. The two ways you can approach this, you can either use L'Hopital, since it's going to be not inconclusive, sorry. It's going to be an indeterminate limit of the nature infinity over infinity. So because of that, you can use L'Hopital here. Or you can just divide each term by the highest power in the denominator, which is n squared. So this is going to be 3n squared over n squared minus n squared over n squared divided by n squared over n squared plus 1 over n squared. You see that 3n squared divided by n squared, the n squared will cancel, leaving us only with a 3 there. And then n over n squared, the n will cancel once, leaving us 1 over n. And then for the denominator, what we have? N squared over n squared. Again, this will just be 1. And then 1 over n squared will remain as it is. So this side we still have the limit as n approaches infinity. At this point, when n is becoming very, very big, approaching infinity, you have to observe that 1 over n will give us 0. 1 over n squared will also give us 0, such that this limit will be approaching 3. And when you look at 3, 3 is finite. So 3 is finite. That part checks out. And apart from that, 3 is greater than 0. 3 is a positive value. So this also checks out. Now, once this checks out, where are we? We're saying that this has checked out as well. So once the conditions have been met, then we can go on and make a comparison. And the comparison being that if Bn converges, An converges as well. If Bn diverges, then An also diverges. Now let's get our Bn. Bn reduced to be 1 over n. And when you look at this, this is the P series. We can check the convergence of this using P series, where the value of P here is 1. So where P is equals to 1. And if you remember from our discussion of the P series, in this case, when P is equals to 1, this just reduces to the harmonic series. And we know the test for convergency here, of course, you have to remember what the test here will be. But with P there being equal to 1, this implies that Bn diverges. So of course, if you have forgotten how we check this, you'd have to check the video on the P series. Okay, so Bn diverges, and since the conditions for the comparison have been met, since Bn diverges, then we can conclude that even our An diverges. So therefore, the conclusion will be to infinity, n is equals to 1 of that sequence we had, which is 3n minus 1 over n squared plus 1. This sequence diverges. So this is how we do it. Now, again, we could have arrived at the same conclusion had we defined our Bn to be equals to 3n over, this is over n squared. Of course, reducing this would have left us with 3 over n, And using this now, let me just show you guys that. So instead of bn, instead of 1 over n, let's say you kept that 3, what would you have ended up with? You would have ended up having the same expression, but instead of 1 over n, this would have been 3 over n. And 3 over n, this would have meant that when you change this to multiplication, this would be times n over 3. And in the end, this ends up giving you 3n squared minus n over 3n squared plus 3. And of course, this is the limit as n approaches infinity. Now, of course, here, by the same technique, n squared into everything. The first term here will be 3. The second term will be minus 1 over n. And then in the denominator, this again will be 3 plus the second term here will be 3 over n squared. Then of course, now we can evaluate the limit as n approaches infinity. As n approaches infinity, this will be 0, this will be 0. So this reduces to 3 over 3, which is just 1. You see that the limit is different from our earlier case. But again, we are not really interested in the limit, we're interested in the conclusions that follow. We see that whether it's 3 like in the previous one or 1 like this one, we still conclude that this is a finite solution and it is a positive solution. Based on this, we can then move on to make the comparison. So again, when you look at our bn, this is equals to 3 over n, and this n, we can actually write this as 3 here, then we have 1 over n. So the convergence of this can be discussed again based on the p series. So based on the p series, we can still come back to conclude that this expression diverges. Since this diverges, even our an diverges. So we see here, regardless of what you would have picked, you would have still ended up with the same conclusion. Now, next up, consider this second example. In this case, again, we want to discuss the convergence or divergence of this series. How do we do it? Same case as before, we define an to be root n over n squared plus 1. And when we reach this stage, we can see to say that regardless of what the value of n is, this will always be greater than 0. We then define our bn. And as n becomes very, very big, you see that the addition of 1 in the denominator will not really change anything. So this will remain as just root n over n squared. When you try to simplify this expression, you should see that this will reduce to just n squared. Let me use a count example there to just help you guys picture that. If I had 3 over 2, this would be the same as 1 over 2 over 3. Of course, these two are the same. Let me just show you why. This would be the same as 1 divided by 2 over 3. And of course, this, when I change to multiplication, this would be 1 multiplying 3 over 2. And you see that this goes back to 3 over 2, which is exactly what we had here. So based on the same trick, if I have 3 over 2, I can write it as 1 over 2 over 3. I'm doing that for one simple reason. You see, I'm trying to use another well-known series here. So this expression, by the same trick, can be written as 1 over, this can be seen as n squared over root n. And of course, I can write root n there as a power. So that's n squared, and then we have n to the power 1 over 2. If I'm dividing same base, it means that I can just subtract the powers, so that in the end, our bn can be seen as 1 over n to the power 3 over 2. So this is what our bn has reduced to become. And when you look at our bn, also, regardless of what n is, since n is from 1 to infinity, you'll see that this will always be greater than 0. So this part checks out. Now, for us to make a comparison, all we have to do for the comparison to be justified, we now have to check the limit as n approaches infinity of an divided by bn. In this case, what do you have? It's the limit as n approaches infinity. What are our expressions? An is, I'll say, n to the power 1 over 2 divided by n squared plus 1. Instead of writing that pair symbol, just use division. And our bn is 1 over n to the power 3 over 2. At this stage, I'll change the division to multiplication. So now I am looking at the limit as n approaches infinity. This becomes n 1 over 2 over n squared plus 1. And then this becomes multiplying n to the power 3 over 2 over 1. Of course, we can multiply these, and when you're multiplying, same base, we just add the powers. So in the numerator, when we add the powers there, half plus 3 over 2, it will reduce to just n to the power 2. In the denominator, this will remain n squared plus 1. From here, we see that by the same trick we used earlier, divide each term by n squared, we're going to end up with the limit as n approaches infinity of 1, n squared over n squared is 1, n squared over n squared 1 again, then this will be 1 over n squared. At this point, we can now evaluate our limit. As n becomes so big, close to infinity, this term here will be 0, so that the solution becomes just 1 over 1, which is just 1. And as we can see, this is finite, and it is positive. Because of that, we conclude that the comparison has been justified here. So if Bn converges, even our An converges. But does Bn converge or diverge? Bn, we sought to say this was 1 over n to the power 3 over 2. Now, the only question you have to see here is, how do you determine the convergency or divergence of Bn? Here, you have to see that we use the p-test as well. So for the p-test, our p here is 3 over 2. And clearly, you can see that p is greater than 1. Because p is greater than 1, we can conclude that Bn converges. And since Bn converges, then even our An will converge. Therefore, the sequence n is equals to 1. And what did we have? We had this expression. So this sequence, we conclude that since Bn converges, so will this expression. So we will converge. So that is done. So let's look at our last example, C. So the approach, again, will be similar to what we've done so far. An is defined to be n, 2 to the power n over 4n to the power 3 plus 1. And then Bn, we see that as n becomes very big, the addition of 1 to the denominator will not really change anything. And the 4 here can also be dropped, as you saw in the first example. So Bn can then be defined as just n, and then 2 to the power n over n to the power 3. And then the n here will cancel once, so that Bn in the end will just be the 2n there, and this will be raised to the power 2 only. So this is what our Bn will reduce to be. Now, once we've reached this stage, we now want to check. You see, our Bn will always be greater than 0. Our An will also always be greater than 0, regardless of what the value of n is. Once this is done, we now want to see if we can use the comparison test here, the limit comparison. And this is by taking the limit as n approaches infinity of An over Bn. Now, what will this be? This is the limit as n approaches infinity, and then our An is n 2 to the power n over 4n to the power 3 plus 1 divided by our Bn, which is 2 to the power n over n squared. Now, how will this work? So in this case, of course, we're just going to multiply these expressions. So here, of course, let's see what will happen. So n here will cancel once with this, and then what will remain with here, before we do that, sorry for that, we first have to change this from division to multiplication. So this is the limit as n approaches infinity, and then this becomes n 2 to the power n over 4n to the power 3 plus 1. Then this will multiply n squared over 2 to the power n like that. Yes, this looks good now. Now at this stage, you can see that since you're multiplying, this can easily divide with a 2n there. so that our expression now remains the limit as n approaches infinity. In the numerator, that is n times n squared, that would be n to the power 3 divided by 4 n to the power 3 plus 1. So this is the expression that we remain with. Again, the same way that we worked it out earlier on, if you wanted to now evaluate the limit for this one, you will have to divide each term by n to the 3. So be the limit as n approaches infinity. Each term by n to the 3, the numerator will now just be 1. 4n to the 3 divided by n to the power 3, this will reduce to just 4, plus this will be 1 divided by n to the power 3. At this stage, we can now evaluate our limit. So as n becomes very, very big, close to infinity, this term will be 0, so that the limit reduces to just 1 over 4. And when you check this, it is finite. And apart from that, it is also positive. So this justifies the use of the limit comparison. So because of that, we can look at our Bn. If Bn converges, then An will also converge. If Bn diverges, then so will An. But that was our Bn. So if we go back to our expression, Bn was selected to be 2n, 2 to the power n over n squared. 2 to the power n over n squared. Now, does this converge or diverge? Well, on top we have geometric series. Down here we have P series. So it will be a little bit tricky to pick one to use here. Instead, we can just go on with the old fashion of evaluating a limit here. Since we know our ability to get the limit here will go hand in hand with us determining whether this Bn converges or diverges. So we'll try to determine the limit of Bn as n approaches infinity. If we try to we're trying to get the limit of Bn as n approaches infinity. If we tried to do that directly here, what you see is that for an expression Bn equals to 2 to the power n and then n to the power divided by n to the power 2, this will end up giving you infinity over infinity. So this is an indeterminate limit. Because of that, we can use L'Hopital's rule in this case. So by L'Hopital's rule, it now implies that this limit can be found by differentiating the top and the denominator separately. So this will be the same as the limit as n approaches infinity of the derivatives. Let's differentiate 2 to the power n. So the derivative of an exponent like this one will be the derivative of the numerator, of the power and the power is n. The derivative of n with respect to n will be 1. Then ln the base. The base is 2. Then we have the 2 to the power n unchanged. So that is the derivative of the numerator. The denominator is n to the power 2. When you differentiate that once, we get 2n. You see, in this case, we still end up with infinity over infinity. If you are to set n to be infinity here, you end up with an indeterminate limit again. So because of that, we can use L'Hopital's rule again. Now here, of course, we keep doing this because we're seeing one thing. The powers in the denominator are reducing. So at one point, we will not have that indeterminate limit. So we might be able to come up with a conclusion. So let's try it one more time. So let's use L'Hopital again. So as n approaches infinity, the derivative this time, again, these are constants, so we'll skip them. We'll just differentiate 2 to the n again in the numerator, which will give us ln 2 from the first derivative. Now the second derivative will also yield ln 2, and then the 2 to the power n again will come out unchanged. When you differentiate the denominator, the solution will just be 2. Now in this case, we see that when we try to evaluate the limit, we will not end up with infinity over infinity or 0 over 0. We'll actually come up with the conclusion. When n approaches infinity, you should see that the top part will become infinity, the denominator will still be 2, so that in the end, this will give us infinity. What is our conclusion here? Here we are seeing that Bn is actually divergent. So Bn diverges. Because we have the limit comparison justified here, since Bn diverges, we conclude that An also diverges. So our conclusion here will be, let's get our An. So our conclusion for this part ends up being, therefore, by limit comparison, AN diverges. Okay, so this is how we use the limit comparison. Now guys, next up, we'll look at the ratio test. See you guys in the next tutorial.